Okay.
Oh, yeah, we have discussed.
We have
Next semester, we have
seminar.
seminar.
Yeah, you also join us.
For a little while before I like became a sensor, I had to like
When is that
do it at a
semester?
certain angle.
I can do it this way.
Maintain contact
Yeah,
with
let's
like
try
the
it one more time.
resistors
It's one
in the
thing, the other
sensor.
one's work.
It was a big pain, so I'd like shake it and then leave it and it pop it out and something so that it would work.
And last one, then just go to the mode where. I don't know. Can you tell me what you do? Yeah, thank you.
If you're gonna use PowerPoint, make a PDF of your slides, just in case.
Well, I didn't have a video yet.
If you export it as PDF, then it'll show.
That's mine.
Not the video,
Yeah.
but
Why won't it show up though?
because PowerPoint.
I've never had any trouble with PowerPoint.
Right. Yeah, it's just this room, I mean, there's, nothing works in this room.
Is that-
This is a totally weird problem with this projector, this never happens anywhere else.
Is that related to the mark size? Because you use larger screen. Maybe you can just crack the window larger.
Maybe it's good enough.
Yeah, how like that? Yeah, there's no volume for whatever reason.
It'll come blaring up the projector.
Yeah,
Yeah, that's fine.
it doesn't connect with the volume for some reason, I'm not sure why. Maybe you can play the volume with yours? I don't know.
Okay,
Yeah.
so what I have made, sorry, is this. So we're shearing something, and this one is a sponge, which is very low stiffness. And we shear it on this surface that have different distribution of this frictional property. And just want to see what's going to happen if we have that. Why did I have to, why did I wanted to build that kind of thing? It's because I, you know, and we all, it's always like 3D. And this is a orthopedic example in 2004 Parkfield. And their co-seismic slip is more like concentrated on some area. And it seems like there are some, these frictional properties are distributed and it's pretty complex. And there are some experiments, and this is numerical experiment, and these numerical experiments were trying to build up some surface that has different frictional properties, some patches that have this unstable patches, and we surrounded by the stable area. Just want to produce that in the laboratory experiment. And why hasn't it been done is because rock is too stiff. So if you want to take, these are the experiments that they want to try to see the behavior of this 2D or 1D fault propagation. And if rock is too stiff, this is the we need this large dimension of this rock to see this nucleation of this fault. And then your nucleation length is known that it's proportional to the shear modulus of the rock, which is about few tens of gigapascal or several tens of gigapascal, which is very big. To see the nucleation, you probably need some meter or tens of meter scales of rock. And there are some experiments successfully. These are pretty recent, and this one is 2013 experiment. And they see this nucleation as because they are softer than the rock. This is PMMA, it's plastic. It's about 10 times softer than the typical rocks. And this is an experiment with the rock, which is 2 meter by 2 meters, which is very big. But they couldn't see, I think they couldn't see the nucleation though, with this, even with this size. So it requires a lot of treatment, and it's very expensive. I think, and then I was thought that if we have some material, but this is salt material, we'll probably be able to see that in a very small scale laboratory experiment. And first I was thinking maybe rubber can do it, and I went to Walmart and found that this sponge, which is here Mr. Clean, and it shows, I saw pretty interesting behavior of this. I wish we had the sounds here. And then these sponges and this desk are stable, and this paper are unstable on the desk. And they're having this, if you have the sound, you have this earthquake sound, like tick, 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 tick. And I found that this slipping can be localized in this patch. So I was thinking that we can build up something more like systematic laboratory experiments apparatus. If we build up something like this, and we apply this sponge, we apply normal stress and shear stress as well. And there are some requirements that the material has to be soft, but it still has to be elastic. And then we should be able to create a normal and shear stress uniformly in it. This way, probably it's not perfectly uniform, and normal stress is concentrated on this side of the shear stress as well. But if you take a look at this part, maybe we can say that it's good enough to have some uniform shear stress. I wish I can have longer, and then that will give you pretty nice uniform stresses near the patch. But I couldn't find longer one, so I just go with this one. And I'm gonna put the unstable patch within the stable surfaces. That's what I use in the kitchen lab, and the rubber. And then I'm gonna measure the deformation at this point near the unstable patch. And there were some initial designs that I was initially thinking about this pole and have arms and move this with the rooters. And I was thinking of U-shaped box, and then I was thinking going on, and this is the final design that I have this mini actuator at it, right here, and then I have this slider and the carriage inside of it, and then I have and this slider is built by this 3D print, and I have this patch rubber, and it's surrounded by this kitchen wrap, which is very thin, so its thickness will not too much effect on it, normal stress or so on. And to get the measurement, I initially was thinking about this flex sensor. So we have this pin, we have this flex sensor, which you push it, and the flex sensor will bend, and I detect, and we can measure it. But I found that the resolution is very low, so I changed my mind to VCDT. It has quite nice resolution. So, and this electric circuit, it's very simple. So I just need to make the current reversely to operate in reverse direction. So I just put two 4 switches. And I have DCDT and separately powered by 30 volt power to maximize the resolution of it. And before I get to the result, I'm going to show you one demonstration, 2 demonstrations in fact. First, it's going to have, this is how I apply this normal stress on it. And if I apply the normal stress, now this thickness of this rubber patch is about a little more than 1 centimeter. I hope it's going to give you a stable slide, because I tested it and it's stable slide. See no sound? It's typically more than 2 centimeters, but we just try to make sure that it's give you stable sliding. But if I increase it to, for example, to make sure like 3 centimeters. And then apply. Normal stress, if I shear you have higher normal stress, you hear the sound. Oh, it gets stable because the normal stress is higher the first time and it gets getting lower. If you're getting even larger, you're gonna have that typically gives you most of these stick sleeps. And if you have larger normal stress, your stick sleep getting larger. And I did one set of experiments with 12 different patch sizes and 8 different normal stresses. I calculated stiffness and calculated the normal force and normal stresses on it. And here's our 2 different results. And here I'm using this ECDT, which gives you a stable sliding in this case. The patch size is 2.5 centimeter in this case. There you see, there it slides slowly, stably, and this is the deformation here. But if you take a look at 5 centimeter patch with high normal stress, you see the deformation, which you can have the sounds here. It's stick slipping, but maybe you can hear that if you're not connected in that. Anyways, so you'll be able to see that this deformation and recurrence time and shear displacement with time. So I calculate the velocity, or some 2-page of results. I calculate the velocity of them. So if you have different patch sizes, and if you have different normal stresses, higher patch size and higher normal stress, you get higher peak velocities of each slip event. The sampling rate is very poor. In fact, it's like 20 microseconds. So the velocity is not exactly the velocity, but it increases with time, with this patch size and normal force. And I plotted this stability of it. This is discussion here. I plotted this stability, the squares are stable, and triangles are mixed up with stable to unstable, like we saw there. And the circles are full unstable. And it seems like I was thinking that critical length of this patch has to be inverse to the normal stress, like this way. But I'm seeing that it's just patch size, and whatever the normal stress is, it always gives you non-stable. I don't know if it is just one set of experiments, or maybe it's because of this combination. You increase the normal stress, resistance can be increased again, proportionally. Or maybe if I run it again, maybe I'm gonna get a different result. So there are a lot of things that I can upgrade this thing. The first thing I want to do is that current resolution is 5 micrometer. That's okay. The sampling interval is 20 microseconds, which is very bad. And I really want to have a longer sponge. And there are some other things. I probably want to use some gouge and stuff like that. And that's what I learned, and that's what I built in this class. So, thank you.
Nice. Questions?
Any questions? No, we don't have time.
I want to see the video play on your computer with the sound so
Oh,
we
yeah.
can hear it.
Yeah.
Because I guess I didn't hear it very well, at least on this
Oh, you didn't?
right now. Did
It's
you
kind of
hear
like
it? I couldn't-
grinding, vibrating.
Yeah, okay, maybe that's what maybe I heard that. It sounded like maybe it was going to be better on your computer.
So here, unstable sliding is this.
Yeah.
This is what we typically have.
Yeah, I can hear it more clearly then.
And I'm pretty sure you can hear it with this too.
Yeah.
Yeah.
Maybe increase the size of the patch. And increase the normal stress as well. More papers.
Very nice. try to calibrate the stress? The normal stress?
No stress.
Do you know what the normal stress is?
Yes, yes. I measure it with a water box and calculate the water gravity.
I have it in the presentation, in fact.
That's fair enough, but oops.
Yeah.
Okay, that's really
Nice. Nice. Other questions? Okay, fabulous, KJ.
Thank you.